So this video is going to cover solely the first section of chapter 1, which is going to be strategies and principles. And we're going to take a look at problem solving. We're going to look at a specific method, Polya's method. We're going to also look at how do we apply fundamental problem solving strategies, and also look at applying basic math principles and using the three-way principle. So this is going to be a very high-level lecture where we're talking about how do we solve things like word problems with clear strategies. So there's 4 steps to George Polya's problem-solving method. The first is understand the problem. The second is devise a plan. The third is carry out the plan. And the fourth is to check your answer. If you think about this method, it's very well aligned with how things happen in the real world. We first are encountered with something that's an issue, and we have to understand what the issue is. Then we have to make a plan to work around it, execute the plan, and then we would want to be sure that we have the right answer. So, a couple of different ways that we can do this would be by drawing pictures. One way we could understand a problem is to take and convert that spatial understanding into an image of what's going on in the problem. This can be a really useful way to helping you process the text that happens in a word problem in math. Another is to visualize a condition. So if I'm talking about 4 campers and I have 4 different people listed, then I could draw those actual people that simulate them shaking hands. And so that will help me have a concrete item to be able to count, to be able to come up with a number of handshakes. And so if I wanted to actually solve this problem, I could actually take and use these points labeled as people, because I am horrible at drawing actual people. So when you draw, you don't have to be an artist, you can keep it simple. And so the intersection points on the lines represents a handshake. So you might be a good enough artist that you could have drawn this and actually drawn the scenario out, but I'm using a little bit of a shortcut because I am not a fabulous artist. The other thing is to choose a good name for what you're looking for. If you don't know what you're looking for, it causes problems. So here's an example. If I assume I have a group of students who are interested in taking Zumba, being physically fit, and another group taking Pilates, I would want to choose names that make sense for representing these groups of people in my picture. And so if I wanted to use, say, a Venn diagram, I would probably label it P for Pilates and Z for Zumba, because I like to keep it pretty simple. And so everyone that takes Zumba would be inside the green circle in region 2. The people who take Zumba and Pilates are in region 3. The people who take only Pilates are in region 4. And the people in region 1 are not interested in being physically fit. They don't want to do either of those things. And the other key is to be systematic. So you want to think it through a series of steps that you can accomplish to arrive at the final answer. That is the piece that often is missed in a math course is, okay, I've drawn my picture, I have my numbers, now you have to make a plan for how to get to the unknown. And so one way of doing this is by creating a list of things to do. So if I have this situation that I'm given here, Nico has 3 options in order to be able to select his new smartphone, and depending on the price he can afford, how many ways can he make this decision? Well, that's not easy to picture draw, but I can make a list that systematically goes through his options. And so I make 3 columns for each of the options, and I label them, and now I can actually count them up. And I have executed a problem-solving plan. That's what's important, is I have a plan and I've executed it. Looking for patterns is 95% of mathematics. If you can recognize a pattern, you're able to use it to answer most questions in a given similar situation. You can also try simpler versions of the problem. So instead of, 4 people shaking hands, you could see what it looks like when 2 people shake hands. Learn from that process and then work on something larger like the scale of having 4 people. And guessing is okay. Guessing and not checking is not okay. So one of the difficulties for solving word problems is that people are very afraid to think out loud. And I think that's something we have to step back from, because how do we learn? We learn from our mistakes. And the only way we can learn from our mistakes in math is by sometimes making a guess and then try and determine, does that guess actually make sense? And that's going to be really important to understand. And then the other piece is most of math is pattern-based, so problems in a similar section are going to be solved in a very similar way. So if you can relate the new problem to what you were doing to the older problem, then you'll be able to make the connection between the two. And that's going to allow you to bridge from one concept to another concept. And so what are some of the mathematical principles? Well, the first problem solving is the always principle. And that's where everyone, the minute they see the word always, everyone's very skeptical, right? Because it's true 100% of the time. And that is typically not the case in the real world. So one of the great strengths of mathematics, though, is we don't deal with partials. So we don't say, oh, this is sometimes true. This is true on Tuesday. We want to say this happens all the time. And so that's one way to understand it. Another way to think mathematically is to try and come up with a counter example. So if someone says the traffic is always terrible on a Tuesday, I would come up with a counter example and say, well, Tuesday at 11 a.m., there's no traffic. So then it's not always bad on Tuesday. There are times that it's not bad on Tuesday. And so that's a great way of trying to refute a math idea, because we're saying this is always true. If you can find one thing that makes it untrue, it actually negates the entire statement. And so we have to be careful then and say that when we say something is false, it doesn't mean that it's always false. Traffic isn't always not bad on Tuesday. At rush hour, traffic is bad. So we can't, if something is true, it's always true. If something is false, it's not always false. We can just think of at least one counterexample. And so the order principle means that when you're reading math notation, you've got to pay really close attention to the order of operations. We've all heard of PEMDAS all day long. We have to do things mathematically in order, or we're going to wind up with chaos and wrong answers. And so while this may not seem earth-shattering in a lot of ways, if we do the wrong thing in the wrong order, you're going to mess up your calculations. So all of those little things that circulate social media, they're like, what do you get when you do PEMDAS here? If somebody makes one mistake on the order that the calculations are done in, you get the wrong answer, and then you've shared it with all of your friends, and everyone's going, I don't think they understand PEMDAS. And the splitting hairs principle is interesting. So when we're reading math statements, we want to really split hairs, okay? So what that means is, if terms are similar, but it seems like they might be just even the tiniest bit different, they don't actually mean the same thing. So in everyday English, when I say equal and equivalent, that means the same thing. It's an equivalent situation, it's equal. But in math, those two things don't mean the same thing. In English, if I mean random, then I literally mean some random person. In mathematics, I mean that I actually made a list and I used a number generator to create random numbers, and then I found the person that corresponded to my random numbers. So wording is incredibly important. And analogies are so important. So if we're trying to look at formal terminology, that's great. We want to use the formal terms as much as possible, but we have to be able to relate them to something in the real life. And so you're going to better understand the math that you're talking about if you can make an analogy like I did with the traffic example. That analogy is much easier to understand. And then we have the three-way principle. So I have a mathematic idea, and then I have three different strategies that approach it. I can use an example, I can verbally talk myself through it, or I can graphically solve it. So those are the three different ways we could address those things. And so anytime we're trying to learn a new concept or to get insight into something new, I can approach it by verbally make an analogy like I did with traffic. Graphically, draw the diagram like the people shaking hands. Or by example, think of an example that illustrates the situation. And that will always lead you to the right place. And, not every one of these approaches fits every situation. The idea is that this section gives you ideas to pull from as you're working on solving application-based problems. And as you start to use these strategies, you're going to find patterns. You're going to find, oh, this strategy works for that problem. And that's going to be really useful to you as you move forward in this course.